Welcome to Mesh Learning's GCSE Chemistry, adapted from Talio, and we're going to be talking about the ever-changing Earth, focusing on continental drift, and then the next lesson we'll be focusing on the atmosphere. So we've got three objectives, and we're actually going to tackle them A, C, B, but these are from the specification. Useful to know what you're supposed to be learning. It's the large-scale structure of the Earth in terms of solid iron core, molten iron, outer core, mantle, and crust. You need to be able to label this up. So we start off with the crust, which is the thinnest layer of the Earth structure, between 5 kilometers to 70 kilometers below the continents. Interestingly, there are some massive lakes underneath the and oceans that are underneath the crust. So where the cracks are formed and the water has gone in underneath, there's actually quite a lot of water trapped in layers underneath and forming massive seas. But if we shrunk this down to the size of a golf ball, it would be smoother than a snooker ball. Right, so all those divots, if you ever climbed up a mountain, well, the size of the Earth just means that it's if you could shrink it down to that size, it would be absolutely beautifully smooth. The next layer is the mantle. Core meaning is the thickest layer of the Earth and contains semi-molten rock. So technically that's called a plastic. So plastic means flexible or fluid, so metals can be plastic as well. So in this case, the rock is actually plastic. It can flow. That's what it means to be. So if you heat a metal up enough, it becomes plastic and is able to flow. So it's more like a liquid, but it isn't a liquid. It's a plastic, solid, semi-molten rock near the core, and this obviously comes out during volcanic activity. Then we have our inner core, the hottest part of the Earth. The temperature can get as high as 6,000 degrees C, and it's mainly made of iron with some nickel. Whereas the central core, the inner core, is the hottest part and can get as high as 6,000 degrees, which in certain parts is hotter than the surface of the sun. Now, the inner parts of the sun are millions of degrees, but the outer crust of the sun, in the sunspots, where they're cooler parts, are cooler than the hottest part of our planet. And it's mainly made of iron with some nickel too. So crust, mantle, inner core, outer core. Crust, mantle, outer core, inner core. Crust, mantle, outer core, inner core. Now, you don't need to know how we know these things, given we've never drilled through the crust, but we have used earthquake data, we've used explosives and very, very sensitive seismometers across the world to be able to map what the different structures are like, because waves follow basic physics principles and they follow laws of physics. So when they travel a particular way, they give us this map of what's happening inside the planet's surface. And this can only be a solid core given the way that this works. And we know this is molten because sometimes it creeps through the crust. So that's really, really critical. So that's a sort of static picture of the Earth, but the Earth is actually moving. Because of that sort of plastic layer of the mantle being heated constantly, when you heat a fluid, that's gases or liquids, you actually get a flow happening. And so the theory of plate tectonics shows that these plates are moving. They're moving about 2 to 5 centimeters a year, which is about the speed in which our fingernails grow. And so the crust in the upper part of the mantle is known as the litho, rocky sphere, and are fragmented into pieces called the tectonic plates. These float on the mantle and move at speeds, as I mentioned before. Now, what is the impact of that? Well, when the so there are two different ways. For a long time, scientists didn't understand how the massive tectonic plates were able to move. I mean, the forces needed are gargantuan, but the power of moving fluids and rock is very heavy. You know, the mantle is incredibly dense and very, very heavy, and so its movement compared to the weight of the crust, and this isn't really to scale, is quite significant. So in the 1930s, some scientists started thinking that convection currents in the mantle caused the plates to move. By the 1960s, most scientists had accepted this idea as being accurate. So plates can either move apart from each other, or they can move towards each other, or they can move alongside each other. So when so if we have a look at these plates here, we have a conservative plate boundary. And at conservative plate boundaries, two adjacent tectonic plates rub together. Friction leads to earthquakes occurring at these plate boundaries. These earthquakes can cause extensive damage to the surrounding areas as well as loss of life. So in certain places like Japan, we have houses that are purposely built. They realize that there are going to be earthquakes. So two consequences of movement of plates are earthquakes, well, actually three: earthquakes, tsunamis, which are massive waves caused by underwater earthquakes or near sea earthquakes, and volcanoes. So where plates are moving apart, a constructive plate boundary, two plates move away from each other, and the resulting gap is filled with magma. So something is being constructed in the middle, and the resulting gap is filled with magma, rises to the surface. The magma will eventually cool, leading to a formation of new igneous rock. So that's crystalline rock, and that's really, really critical for a piece of evidence, because if these move far enough away, well, look, there's going to be the same rock on both sides. But if this keeps moving away and keeps moving away and keeps moving away, that rock and that rock will be the same. So that's really, really critical. Just keep that in your head when we come to how do we know, right? Just think about that for a second. If a volcano produces rock here and here, then they're going to be identical types of igneous rock. So destructive plate boundaries, another type of plate movement, is where they move together and they can either bulge upwards, forming mountains, or one can subduct under the other, which is what we're seeing here, leading to the one plate being destroyed underneath. The destructive plate boundary, an oceanic continental plates move towards each other. The oceanic plate is forced under less dense, lighter continental plate. The sinking oceanic plate slowly melts as it sinks, forming a pressure buildup of magma, which results in volcanic activity on the continental plate. Right, so we have places like Bath, which are sort of in the middle of plates, and yet they have volcanic activity because there would have been stresses which cracked through the crust and created volcanoes. So evidence from the past. So have a look at this exercise to try and get you to think about what type of plate boundary, what is it caused by, what does it result in, and what is it also known as if it has an alternative name. So just either write down recreate this table and then put them in the correct places, or just put a particular 1, 2, 3, 4 for the different things. So here are the answers. So you see, conservative plate boundary is caused by plates rubbing together and results in earthquakes, known as, well, just conservative plate movement. And then we've got destructive, where the plates collide together, volcanoes, earthquakes, and there's a convergent boundary. And then constructive, where the plates move apart, new igneous rock is formed, and we get a divergent boundary. So here's a question to try. It's from an exam paper. Briefly outline the theory of plate tectonics and use this to describe what happens at one type of plate boundary. So that's all the stuff that we've just talked about. So here is an example answer. You can see here that there are some mistakes. So you've got to put keywords in there sometimes. So convection currents was needed instead of the movements of the mantle below. The convection currents are the critical thing that is needed. They're being moved by the convection currents of the mantle below. When the plates at a constructive boundary magma rises into the gap, this magma will cool and solidify into new igneous rock. Critical that you put the word igneous, that's what they're looking for. Right? So keywords: constructive plate boundary, convection currents, igneous. Make sure you're getting those words. If any of those words are not really clear to you at the moment, go back and watch the rest, because we're gonna push on now and look at the next objective. So we're going to look at continental drift. When the Earth was very young, the arrangement of continents looked something quite different to what it is now. So we called this supercontinent Pangaea, and there were a lot of animals. This is about 225 million years ago, and a lot of before that. Obviously, if you didn't have animals on land and you didn't have lots of things getting fossilized, you wouldn't have much evidence. The rocks would give us some evidence as to where things went pre-Pangaea, but this is a fairly early part in the life of plants and animals. So continental drift looks a little bit like this. So we can see the continents spreading out, and this is happening over millions of years. Because it happens so slowly, it's one of the reasons why it took scientists so long to take these ideas on board. Scientists think the map of the world consists of one supercontinent called Pangaea, as we mentioned, and over the course of the Earth's history, the continents have drifted apart from their current position. So we can see here that continental drift occurred from the evidence that we have occurs from about 225 million years ago, 150 million years ago. So we can see this supercontinent Pangaea, and then we've got Africa and South America, we've got North America, we've got Europe and Asia. And so this then turned into Laurasia and Gondwana land about 150 million years ago. So these are still very close together. Look, South America and Africa, very, very close together by comparison to how they are now, and they are moving further and further away from each other. India and Africa around here. Now, what you don't need to know is where stuff was, but you need to have an appreciation of what things look like. So you can just look at the distances between the different land masses to tell where things are. So Alfred Wegener was the first scientist to suggest the idea of continental drift in 1914. Wegener thought that all the continents were once joined together, but had drifted apart over the course of Earth's history to their current position. So some evidence. Now, there are three pieces of evidence you need to be able to quote for the exams, and you could have a 3 or a 6 mark question. But the continental shapes, if you go back to this image here, you can see that they fit together. Did they ever fit together? Yeah, absolutely they did. It's weird that they look similar shapes, because they did. But more importantly than that, and I mentioned this earlier, was about the rock shapes. We'll come to that in a second. We've also got fossils as well. So fossils, if you're not clued up on that, are animals or plants that have been covered over by something which prevents them from fully decaying. There are bacteria and fungi and all sorts of microbes, and actually macroorganisms as well, so like carnivores, that will get rid of the remains. But if they fall into something like a peat bog, there's not much oxygen, and so they may be preserved, and then squeezed and essentially calcified, turned into rock, so that we can then dig them up. Now, where the animals are similar, where we find these similar sorts of depth being fossilized in two different continents, there must have been a particular similarity, because when animals are in isolation, they tend to evolve and be successful in their own environment, and they tend to change over time. So when we've got fossils and they're identical animals, it gives very strong evidence that the places were next to each other and had a bridge which facilitated animals being on both sides of that bridge. And then that bridge got cut at some point. And then finally, as I mentioned earlier, the rocks. So we find that rock structures are very, very similar. So this igneous rock coming from volcanoes will be similar in composition, chemical composition. Depends on where they are and what occurs, and also maybe radioisotopes that got caught in them will be of a similar age. So there's a lot of information captured within all of this stuff, and you need to be able to quote continental shapes, fossil remains, and rock structures. So obviously, here are just some summary points. Continental drift was Alpha Wegener, hottest part of the Earth's core. Which type of rock is formed? Igneous rock. How far do the tectonic plates move in the course of a year? 2 to 3. Well, 2 to 3 is acceptable. We said 2 to 5 earlier, so that's well within that boundary. It's definitely not meters. It's very, very slow, which is why it took so long for scientists to believe it. Okay, so here is an exam question. I need to try that exam question. So here is the answer. Put the letters to the diagrams in the correct order. 225 million years ago, C, then D, then A, then B. Describe two pieces of evidence that Wegener used to support his theory. Obviously, there are three. We mentioned them. Close fit of coastal lines, South America and Africa. Similar fossils across continents. Similar rocks. But you just needed two of those. And Wegener's idea was accepted in 1960 and led to the theory of plate tectonics. Which of the following events is likely to occur at a boundary where two plates slide past each other? Well, that's earthquakes, and that's conservative plate boundaries leading to earthquakes. Now, you might get earthquakes happening where you've got destructive interference and things like that as well, but you're much more likely where they're sliding past each other, like in San Francisco and the San Andreas Fault. So we have looked at large-scale structure of the Earth. We've looked at the theory of plate tectonics created by Alfred Wegener, and we've looked at the processes occurring at conservative, destructive plate boundaries where they slide past each other.